Let's have a look at the FLOEFD interface. FLOEFD uses an OEM version of SolidWorks, which allows building parts and assemblies quickly and efficiently. Note that FLOEFD is also available as a fully embedded software within the Pro Engineer and the CATIA environment. Other native CAD data, such as Inventor or Solid Edge files, can be easily read and used in FLOEFD. Getting back to the turbocharger analysis, you can see on the screen that all the parts needed for the model definition are already in place. The revolve with the static variable vanes, the turbine, and the inlet and exit sections. So, how do we take advantage of this existing CAD geometry and define a rotating airflow analysis? First, we will run the wizard. The wizard is a great way to define the overall boundary conditions of the problem and get it ready for the flow and heat transfer analysis. The wizard helps us navigate through various required steps. The first step is a name for the configuration that you are defining. Let's name this configuration baseline and add a brief description of the project. Since FLOEFD runs from within a SolidWorks environment, this project will create a new configuration for the current assembly. Next, FLOEFD will ask us about the unit system that we would like to use. For this model, we will set the pressure in PSI, the temperature in degrees Celsius, and the velocity to feet per minute. Note that the volume flow rate will also be changed to cubic feet per minute. Keep in mind that even after finishing the wizard, you can change and customize the system of units at any time. Next, we will need to specify the type of analysis that we would like to run. For this flow problem, we'll choose internal since we are only interested in looking at results within the turbocharger. If the goal was to look at flow over a wing, then we would choose external. Exclude cavities without flow conditions is a smart way for FLOEFD to filter any unnecessary gaps which could be part of the CAD geometry. Heat conduction, convection, and radiation do not need to be included for the simulation. In our case, we will be using the rotation model. We are just interested in local rotation since only the turbine rotates. The following wizard choice is for the fluid properties. FLOEFD comes with a pre-populated engineering database which makes it quite easy to select a fluid. Let's select air for this example. All the physical properties such as density, viscosity, specific heat, and thermal conductivity are already defined. Note that FLOEFD supports some fluid mixing capabilities as well. For more information, please check the Mixing Processes application page on our website. You will also notice the flow type is set to laminar and turbulent, so FLOEFD can decide what the flow regime is in various sections of the turbocharger. There is no need to consider additional friction at this point, so we'll leave the solid walls as smooth and just move on to the next step. Before we get into the mesh definition, we will set up the initial conditions. These are very important to define, especially if you are doing a time-dependent solution. For the turbocharger, we will change the fluid temperature to 900 degrees Celsius since this is the inlet air temperature. Finally, the wizard will help us select a mesh resolution. As you can see, the default setting is 3. For the turbocharger simulation, we'll select a level of 6, which will help refine the mesh in areas of interest, such as the turbine. To ensure even more refinement, especially between the vanes and the turbine inlet section, we will select a minimum gap size of 3.3 millimeters. This value will help the mesher identify the smallest dimension that needs to be captured for the analysis and create the corresponding grid. Once the wizard closes, you will see black lines show up on the screen. These lines follow the boundaries of the computational domain. That's a quick way to verify that FLOEFD recognizes the actual fluid and solid volumes that need to be analyzed. Now that we feel confident about the fluid and solid volume definitions, let's finish the model setup. First, we will make the turbine rotate by defining a rotating region. This requires building an artificial part that encompasses the volume where the rotating coordinate system is used. So I created this blue-green part called rotating region, which is just an axis-symmetric solid surrounding the turbine. Let's set this part to rotate at 8,000 RPM and make sure it's rotating in the correct direction. Then, FLOEFD will treat everything sitting inside this volume as if it rotates at 8,000 RPM. We will now need to focus on the airflow conditions. To set up the inlet flow condition, let's zoom in on the inlet lid and select the interface of the lid. Once selected, we will be able to apply a volume flow rate of 124 cubic feet per minute. The default pressure of 14.6 psi is applied to the inlet. Note that this could be changed if it was different from the initial conditions. Once the inlet flow boundary condition is applied, FLOEFD highlights the flow direction in the display area using red arrows. Similarly, the interface of the exit lid is used to define the exit flow boundary condition. In this case, the pressure is set to be the default value of 14.6 psi. Before solving, we need to remind ourselves what the analysis objectives are. One of them is to calculate the torque of the blades and the turbine. So how can we set that up in FLOEFD? That's where goals come into the picture. Goals help the user do results analysis in a very efficient way. Goals are also used by the solver to speed up convergence. As you can see, output variables can be reported on the point, a surface, or a volume. To monitor the blade torque, we will create a surface goal and select one of the turbine blades. Other goals defined for this project include a global goal to monitor the turbine torque and additional surfaces goals to report pressure and velocity at the entrance of the turbine. An equation goal is also set up in order to monitor the turbocharger pressure drop. This case is now ready to solve. Let's have a look at the solver options. An important feature is to be able to run the solver in the background and, while it is solving, being able to work on another FLOEFD model. This can be done by running the solver as standalone. As you can see, FLOEFD can also take advantage of multi-core or multi-processor speed to reduce solution time. Let's start the solver so that you can see how FLOEFD generates the mesh and the results. FLOEFD uses an octree-based mesh which generates fluid, solid, and partial cells. The partial cells are cells that get divided between the fluid and the solid to better match the geometry. FLOEFD's powerful rectangular adaptive meshing approach is a core strength of the software and can be transparent to the user if desired, but it is not limited to being a black box approach. Optionally, advanced users have full access to the meshing controls for fine-tuning. During the run, the engineer can get real-time feedback about its progress by looking at the goal values. You can also preview a contour plot such as the pressure distribution through the turbocharger in the turbine, which gives you a good sense of how the solution is developing. Once the goals converge, the solver will automatically stop. This model takes about 4 hours to solve on a 64-bit 8 GB of RAM dual-core processor machine. We can start the post-processing by looking at the pressure distribution in the turbocharger. To do so, let's create a plot cutting through the top. So, on this pressure plane, we can see there are low pressure areas on the downstream sides of the guide vanes. These behave similarly to airfoils, with a high pressure stagnation point on the nose and a low pressure upper surface. We also see there is low pressure in the turbine. Remember, this is a turbocharger and the purpose is to extract energy from the exhaust and use it to drive a compressor that will compress the intake air to the engine, therefore improving engine performance. Let's display the mesh which was used to solve this model. Because the mesh was set to a level 6, it automatically activated the solution adaptive mesh. This functionality enables the solver to pause periodically during the solution and add mesh where there are high gradients in the variables like pressure and remove mesh where the gradients are low. For example, you can see that there are smaller mesh cells in the areas behind the guide vanes where the flow field is more complex. The result's accuracy is therefore improved. Keep in mind that this plot can be annotated with pressure values at various locations, which could help highlight problematic areas. This view can then be exported as an image file to be included into a report or a presentation. We are also interested in what is happening on the turbine surface, so let's create a surface plot. We can look at any parameter on the surface of an object, even velocity. Velocity is equal to 0 on the surface, but the FLOEFD surface plot has the option of offsetting the plot slightly away from the surface so that the near-wall velocity is displayed. So far, we only looked at two-dimensional or surface plotted results. How can we get a 3D view of the flow through the turbocharger? That's where flow trajectories come into picture. Let's track the airflow movement from the inlet. Setting up the number of trajectories defines the number of streamlines that we would like to display. Changing the shape of the trajectories to arrows helps visualize the flow direction. Finally, we chose the color of the streamlines by velocity in order to see how the airflow is accelerated through the turbine. The streamlines can be displayed as static or can be animated. Animating the flow is an efficient way to understand the dynamics of the fluid. It could, for example, emphasize a flow separation region. Note that these animations can be exported as video files. FLOEFD can also extract the flow rate, pressure, and forces out of surfaces and volumes. For example, let's select the turbine. When a surface parameter is created, it will report various things such as the minimum and maximum pressure for this surface. The reported data can be exported directly to Excel. Then you can clearly see the values of the force applied by the fluid on the turbine along with the torque. Finally, if you recall when we defined the model boundary conditions, we set up some goals such as the pressure drop through the turbocharger. Since these goals were nicely predefined, they can be easily reported into an Excel spreadsheet. We can then read the torque value from various turbine blades, as well as the average velocity and pressure entering the turbine. FLOEFD also creates a plot for each goal versus the number of iterations, which shows when the goal reached a stabilized value. FLOEFD also offers an integration with Microsoft Word for an automatic report generation. The report gets created from a predefined template and summarizes all the model input data, such as the computer on which the model was run, the boundary conditions, the solve time, and finally the results with the goal's values. Furthermore, any plot created earlier can be added on the fly to the report. This is a great way to share results with customers. The analysis of the turbocharger is now finished. Let's assume that we would like to make changes to the model. For example, we would like to modify the RPM of the turbine or the volume flow rate. We could also be interested in changing the vane angle to see how it impacts the torque and the pressure drop. In FLOEFD, you can easily make a copy of an existing project by using the Clone Project option. A new configuration gets generated within the CAD environment, and all the FLOEFD settings are copied over for a new analysis. Then you could edit any of the input data or select a geometry tolerance, such as the vane angle, to enter a new value. Once you define the new project, you will need to run it to get a new solution. Then, since all the configurations get saved in the Configuration Manager, you will be able to compare the results with the previous runs and draw conclusions on the design. This concludes the Variable Geometry Turbocharger presentation. This demonstration focused on the FLOEFD standalone software, but keep in mind that FLOEFD is also available as a fully embedded software within ProEngineer and CATIA. Thank you very much for your interest in FLOEFD.